Okay, we're going to go through Competency 8, Renal Physiology. You will find information from pertaining to renal physiology in your OpenStax Chapter 25 and Patent Chapter 42. I'm going to go through this video compared to the last one is going to be quite a bit shorter. The kidneys and the urinary system as a whole were studied in general A&P. So I'm just going to do a quick review of the anatomy of the urinary system. My main focus is really to discuss some of the basics of the physiology or function. So the kidneys are the principal portion of the urinary system. The nephrons of the kidneys and some of the blood going into and around and through the nephrons are what our focus is really going to be on today. We include certainly the ureters, the urinary bladder, and the urethra as part of the functional aspects and of elimination of urine, and certainly those are structures you're all familiar with. The right and left kidneys, and let's see, get on with it here so we can get to the physiology portions, but we look at the kidney from a frontal section or a coronal section. We can see it's broken up into the cortex and the medulla. That cortex is going to be the more superficial aspects. That's where the bulk of the nephron structures are going to be located, or the bulk of the structures of the nephron are going to be located in that cortex area. We do see the loop of Henle dip down into the medullary region of the kidney, and we see those renal pyramids being the defining feature of being in the medullary portion of the kidney. So again, cortex, more superficial than medullary. Within the medullary, we are going to find the loops of Henle, but we're also going to see those areas as being where the urine is initially collected and dumped into these minor calyces, and then the major calyces till we end up in this renal pelvis area. Okay, so we see the major calyces, and these are the minor calyces, these little buggers coming off of here. So anyway, into the renal pelvis, and then finally past the hilum area and into the ureter. Let's see, blood vessels. Again, I'll pause on these for a second. You can read the black and white of it, some of the review of the structure, a review of some of the structures that we looked at in general. So what I just went through, but in black and white print there. Highly vascularized, of course. We think of the renal artery as being the primary deliverer of blood to the kidneys. So the blood that goes to the kidneys, it not only supplies the kidneys with a medium in which to form urine from, is the renal artery. It's what brings that in. The kidney tissues and cells certainly are able to receive nutrients from that renal artery. Renal vein taking blood certainly low in oxygen away from the kidneys. And this blood is also going to be hopefully a little less full of a variety of items that maybe are less desirable. So anyway, which we'll look at. We're going to look at the components of urine, how urine is produced. Let's just keep going again. Those structures you can take a look at. Micturition is the process of the creation of urine and ultimately leading to the release of urine. So, what produces the urine are little structural the smallest functional unit, smallest structural unit of the kidneys, known as the nephrons. Nephrons are, and again, we did look at these. You were tested on structures of the nephrons, so we're basically just going to add a couple of functions to these these regions and microstructures of the nephron. So anyway, we have the corpuscle and the tubule. The renal corpuscle is where the initial action happens. This is where we find the glomerulus, which is going to be the capillary network of the nephron. And again, whenever we see capillary anything, we're thinking immediately that something is leaving the blood and something is going into the blood. There's some sort of transfer of goodies at that spot. Now, any time you hear capillary, okay, so the majority really of this semester is focused on the cellular and chemical levels of organization. And in order to get the chemicals to the cells of the body, it's the bloodstream via these capillary networks. So dropping everything off that needs to be dropped off, picking everything up that needs to be picked up. These are macromolecules, vitamins, minerals, hormones, enzymes, other chemicals. So the glomerulus is the name of the capillary network where blood is coming from the renal artery and branching till ultimately getting to a nephron. So anyway, the first portion is called the renal corpuscle, made up of that capillary network called the glomerulus, which is tucked inside of the Bowman's capsule, that also known as the glomerular capsule. So this is the corpuscular area. Okay, so we're going to see kind of a double wall with the Bowman's capsule. And again, it forms kind of a glove around, you can see the Bowman's capsule here. Again, kind of the peel or the shell protecting and around that glomerulus. So as blood travels into that capillary network, we're going to see a variety of items passing across that glomerular capsular membrane. So anyhow, we'll look at that more closely as we go. I'm just going to give you some black and white of it. Again, this is generally a review, I think, for most of you. There are little windows or fenestrations or pores in the capillary walls to allow filtration to occur. One of the main components of what we're studying in this competency are the functions, the three functions of the kidneys. Filtration is function number one. So the first thing that occurs regarding the functional aspect of the kidneys is occurring right here in that corpuscular area where the glomerulus is nestled inside of the Bowman's capsule. This is where filtration, or step one of the creation of urine, is going to occur. Okay, filtration, step one, glomerulus. All right. And how do we get substances out of the capillaries? Through what we call fenestrations or pores in this particular spot. Okay, we have mesangial cells located between the glomerular capillaries that are, again, primarily structural and support features to keep that glomerulus tucked in and anchored inside of that Bowman's capsule. And then again, so we have glomerulus or the capillary, some supporting cells in the space between the capillary and the glomerula and the Bowman's capsule or the glomerular capsule. Again, we're going to see kind of an endothelial membrane, a basement membrane, and then a visceral layer forming this Bowman's capsule. So we'll look at that coming up in a little bit more detail. Again, you can review this. OpenStax and Patent's text both have good illustrations of these tiny little features. So here's one of them from Patent that I pulled out. So here's the capillary network. We can see of the glomerulus, we see the plasma and the red blood cells, and then we have these little windows or pores or fenestrations in the capillary wall. And then we have this basement membrane that's connecting the endothelium of the capillary and the capsule itself, the Bowman's capsule. Okay, so we see the endothelium of the Bowman's capsule and the endothelium of the capillary linked by this basement membrane. Okay, so we can move what's called filtrate through these pores. Okay. And then we have these little grooves called filtration slits in the Bowman's capsule. And the Bowman's capsule also has these little podocytes or podocytes. These are little feet that certainly help with stability, with anchoring and structural integrity. Pardon me. Okay, so we'll keep moving. The renal tubule. So we'll talk about the functional aspects here in a few minutes, but filtration occurs first. The first step of urine formation is filtration, and that occurs here at the Bowman's capsule with the glomerulus. Now, that's the end of the corpuscular aspect. The second aspect, or the rest of the action occurs, is called the tubular aspect. So we're going to see what's called and again, these should be review for you. Proximal convoluted tubule, down descending loop, looping around the loop of Henle into the ascending loop and out to the distal convoluted tubule into the collecting duct. So those terms should be familiar with you or familiar to you and should be with you and your long-term memory. So if they weren't etched into your long-term memory in general, please take time to etch those in. These are terms that really you're going to be familiar with clinically, certainly on the NCLEX when it comes to urinary system structure and function. Really with urinary system structures on the NCLEX, again, you want to remember right and left kidney, right and left ureters, urinary bladder, and urethra for the macro areas. And then as we break down the kidney, we look at the cortex being the more superficial layer where we primarily find the nephrons, and then that medullary aspect where we find the renal pyramids, the minor calyces, major calyces into the renal pelvis. And then deeper in, we get to the nephron. This is where the formation of urine is occurring. It's the smallest functional unit of the urinary system, comprised initially of that glomerulus or that capillary network surrounded by a Bowman's capsule or a glomerular capsule. The first step of urine formation occurs there, called filtration. So those are the basic concepts and structures, I suppose, that you're going to have to be aware of when it comes to functional aspects. I'll discuss briefly what filtration is, and the other two uh, 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 functional features in regards to urine formation. So, where does filtration occur? Glomerulus and Bowman's capsule. Okay. Now, how does it occur? What happens? We'll talk about that in a few minutes. Second item, second structural aspect as we leave that Bowman's capsule, as we're going to connect and form that Bowman's capsule into a tubular system. Proximal meaning closer to, convoluted meaning there are a lot of twists and turns, tubule meaning it's some sort of small tube. So proximal convoluted tubule, descending into a loop, ascending towards the distal convoluted tubule. Okay, again, you know that should all be a review. If it's not, it's understandable. You're not studying this stuff constantly. However, again, it's very important to know the basic structural setup of a nephron. I know the terminology is a little bit strange, but by now it should be familiar to you. And why do you need to know the structures and where they're located and the order in which they go? Because then when we discuss the function coming up now, you can envision and see where these functions are taking place. And we don't have to reinvent the wheel and go back through struggling with the basic terms of the structures. So the functions will be easier to understand if you have a good grasp on the structures. So again, I urge you, if this has been confusing up to now, to pause the video and go back and look through these structural features. So anyway, moving on. Proximal convoluted tubule, descending loop into the loop of Henle, and getting to the distal convoluted tubule and terminating at the collecting duct. Now, we do see at the distal convoluted tubule the specialized item that you may have looked at briefly or discussed in general A&P. The juxtaglomerular apparatus is going to be located along with the afferent arteriole and the distal convoluted tubule. This is an area where we can get some last minute, last second, really, reabsorption or secretion to occur. So keep that in mind. We'll be looking at that in more detail shortly as well. And the distal convoluted tubule, the juxtaglomerular apparatus or cells, as well as the macula densa. So we'll look at those two items in this particular area shortly in regards to its function. Okay, so again, blood supply of the nephron. So we're going to start getting into some of the functional features coming up. But before we do, you want to also remember that specifically the afferent arteriole is going to dump into the glomerulus, and the efferent arteriole is going to leave the glomerulus. So you definitely want to remember that. All right, so let's take a look at a nice illustration. We've got a renal artery and a couple of branches off of that renal artery, and then we get our first afferent arteriole, which is going to travel and again terminate in the glomerulus. You can follow the arrows of blood flow to help as well. So, step one of urine creation is going to occur at this glomerulus Bowman's capsule spot. So, we're going to get some filtrate. We're going to get some stuff out of the blood. So, we'll talk about that, what that stuff is here in a few minutes. And we're going to have that filtrate or urine traveling through this proximal convoluted tubule, this descending loop, ascending loop into this distal convoluted tubule. And you can see we've got the juxtaglomerular area over here. So we'll take a closer look at that coming up as well. And then finally, we get the termination spot of the nephron at that collecting duct where that distal convoluted tubule is going to dump. You can see there are other connections where other distal convoluted tubules from other nephrons have deposited the urine. And then we see that the collecting duct is going to be part of the renal pyramids, and those are going to connect with and dump into the minor calyx. Okay, another item we see, so that's the so we're basically following two pathways of fluid with a nephron. We're following the pathway of urine and urine formation within that tubule network. And then we're also following the blood and the blood supply and the capillary networks, because we're going to see two capillary networks associated with a nephron. And again, capillary means something's going into or coming out of the blood or both. So glomerulus, afferent arterial going in, efferent arterial leaving. Now, let's follow that efferent arterial out of the Bowman's capsule. We can see that there's a fork in the road. Hey, and that the one fork is going to go up and around. That's we're going to see that juxtaglomerular apparatus associated with that, and then we're going to travel along that efferent arterial, and we're going to end up back over here, okay, in uh, uh, the venous supply network, okay, ultimately to the renal vein. Okay. Now notice too, um, we've got quite a bit of action down here, and then we've also got quite a bit of action around these, particularly the proximal convoluted tubule, as well as that loop. Now let's go back up to the efferent arterial and go to the other fork, the fork that descends. And we end up getting a whole bunch of little capillaries that are intertwined with the tubular network of the nephron. Okay. These are called peritubular capillaries around the tube capillaries. Okay, so again, with a capillary, we can drop things off, pick things up. The other thing you want to pay attention to is this interstitial space, especially when we get to this loop of Henle. Interstitial space is the space in between the capillary and the tube, or the capillary and another portion of the capillary. Okay, all of this negative space where you see white in there, that's going to be interstitial space where we're going to find interstitial fluid. So as these capillaries are dumping product off to potentially be pulled into the tubular system, secreted into the tubular system, we can also be potentially pulling or reabsorbing things out of the tubular system and putting them back into the bloodstream. Okay, so we can take things back out of the blood just like we did up here. In the glomerulus, we can continue that process anywhere in these peritubular capillaries. Okay? And at the same time, we can put stuff back into the bloodstream that maybe got pulled out up here, or maybe got pulled from the interstitial space, or needs to be pulled from the interstitial space. or pulled from the tubular network. So either way, or however we do it, we can potentially pull things back into the bloodstream or reabsorb items back into the bloodstream. We see a lot of reabsorption going on in the proximal convoluted tubule. You can see how that proximal convoluted tubule has quite a bit of this capillary around it. And this would be, especially because it's the more on the venous end, this is where we would see some reabsorption. So if anything, or not anything, items that we're going to find in the filtrate that left the bloodstream in the glomerulus are going to get reabsorbed into the bloodstream, into this paratubular capillary network. And you can see how it's illustrated here, that this end of the capillary network of the paratubular capillaries would be a great spot to dump things or take things out of the tubular network and dump them back into the bloodstream. Okay. So we can continue with that reabsorption process. So that's function number 2, reabsorption. Okay. Filtration first. Reabsorption is pulling anything from proximal convoluted tubule or the loop of Henle and putting it back into the bloodstream. Okay. We can also do it in the distal convoluted tubule. So reabsorption primarily is going to be at the proximal convoluted tubule and some down into the descending loop and the loop of Henle. And again, we'll look at what may need to be reabsorbed or pulled out of. Well, for instance, like sodium. What's getting pulled out here? Sodium, water, glucose, potassium, calcium, chloride, basically anything we've talked about up to this point is potentially going to end up as filtrate in the urine, and we don't want glucose in the urine. We don't want high levels of sodium in the urine. We don't want certain proteins in the urine. There are things that we just do not want to show up in the urine, or if we see it in the urine, we want it to be in very low regulated levels. So if in this glomerulus we pulled things out that needed to stay in the blood, that's fine. We can reabsorb them in any of these areas, particularly the PCT or the loop of Henle. Now, as we continue on this path and continue to look at these paratubular capillaries in the loop of Henle and now the distal convoluted tubule, the third process called secretion can take place. So if there are items in the blood, especially right in this area, if there were items in the bloodstream that we were unable to filter out, maybe these fenestrations, pores, windows, maybe these interlobular area, or these little crypts or grooves in the membrane of the endothelial membrane of the capsule were clogged, or we were just unable to get things out or filtered out of the blood into the Bowman's capsule. So as the blood leaves that Bowman's capsule, we have what we call the efferent arteriole. That can, whatever's in the blood that maybe should have been pulled out of the blood that didn't get pulled out here, can get secreted into this interstitial space. Okay, so you can see all that interstitial space, and it can get secreted and taken by the distal convoluted tubule or this loop of Henle and this ascending loop. So we can, step 3 or process number 3 of urine formation is secretion. We can potentially secrete things out of the blood into the tubular system for removal from the body. So this juxtaglomerulus, and this is a good spot to do it because again, as you can see, it's going to take things right out and put it into that venous system. Okay. So so basically the next few minutes, several minutes, we're going to go through uh, those three processes, those three processes of filtration, reabsorption, and secretion. So the chief function of the kidneys certainly is to process blood, specifically plasma of the blood, and form urine. Okay. Filtration, again, moving water and protein-free solutes. Okay, solute means something that is contained within the solution, some sort of usually it's a solid, it could be a gas, um, that's going to be contained within the plasma of the blood. So primarily thinking of ions and gases. Protein-free solutes. So the idea is so amino acids are not going to be traveling out of the glomerulus and into the Bowman's capsule. Okay, tubular reabsorption. Again, we can anything that got into that tubular network as filtrate, we can pull it out of the tubular network and put it back into the bloodstream. Secretion, if there are items in the blood that we really do need to get out of the blood and eliminated from the body, we can secrete out of the blood and into the tubule for excretion. The kidneys are receiving about 47 and a half gallons of fluid a day. So, whoa, they're busy. All right. So this is a nice little illustration. We can again see that afferent arterial coming in, Bowman's capsule. We can see filtration occurring. And as we go, we can see the reabsorption of water. So we're going to reabsorb a lot of the water that got pulled into the tubular network. We're going to pull sodium. And again, notice too, we're at this proximal convoluted tubule. Glucose, any glucose that got in here, we're going to see a co-transport mechanism in a little bit of sodium and glucose. Sodium, by the way, is going to require a pump. So there's a lot of sodium potassium pumps located in this tubular network because as much sodium that might be in this tubular system, there's still a higher concentration of sodium in the blood typically. So we do need ATP and sodium potassium pumps to get sodium out of these areas and into the bloodstream. So anyway, glucose is another reabsorption item. Notice still no secretion yet. So we're going to go down that loop. We get over to the proximal or the distal convoluted tubule, and we see urea. About half of urea is going to be eliminated, and about half is going to be secreted, about half reabsorbed. Okay, so we're going to see any over here. So 50% of urea is gone by the time we get here. By the time we get to the distal convoluted tubule over here, there's still quite a bit of urea, ammonia, nitrogenous waste that's going to be contained within the blood. So we do need to secrete or eliminate any of that excess nitrogenous waste. Okay, so that's the first areas where we do see secretion going on, or in the primary areas. We see again reabsorption of water, reabsorption of potassium at this spot. We also, at this distal convoluted tubule and collecting duct, notice we've got hydrogen ions showing up onto the scene. Whenever we see, we haven't talked about this a lot yet this semester, so this is kind of your introduction to pH and pH balance. This chapter, I'm going to touch on it briefly right now, and then next chapter on perfusion, respiratory system, gas exchange, competency 9, we're going to talk about hydrogen ions again and pH, and then we're going to the last module gets into competency 10 and 11, which go into digestion and assimilation and nutrition as well, and then we get into pH balance, fluid balance. So we're going to come back to this stuff, particularly in regards to hydrogen ion concentration. Like really the rest of the semester. So here it is, your hydrogen ion concentration. Hydrogen ion and pH go hand in hand. The little p, big H, the big H is for hydrogen ions. On the pH scale, the lower the number, so a pH of a 1 or a 2 or a 3 is considered to be acidic, and that means the lower the number we have, that means the more hydrogen ions we have. So it's a little bit counterintuitive initially. So I want to introduce you to it now because we're going to see it quite a bit over these next 3 or 4 weeks. So hydrogen ion concentration, when it's high, the pH number or value we assign is going to be low. So, so the higher, the more hydrogen ions, the more acidic something is. So we see hydrogen ions being secreted from the blood. So what we're doing here is regulating the pH of the body, and particularly the blood, which is usually at around a 7.4, so slightly basic even. 7.0 is the neutral number we assign. It's not a sign, it's a base 10 formula. It has to do with hydrogen ion concentration, and how much of it is based on a negative exponent operation. So 10 to the negative first, or 10 to the negative 1 is going to be 0.1, and 10 to the negative 2 is going to be 0.01. 10 to the negative 3 is going to be 0.001. So the negative exponent, when you look at a base 10 formula, has to do with powers of 10. So any exponent with a 10, if it's a positive exponent, you're just adding zeros to the end of a number. So 10 to the 0th power is 1, 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1,000, and so on. When you see a negative exponent, it just means we're moving the decimal and making a smaller and smaller number. So the negative exponent, whatever that number is in the exponent with a negative in front of it, that's how many times away from the decimal we are. So the higher the negative exponent, the smaller the number. So anyway, that we'll talk more about pH in detail, but I do want to introduce you to it. So the blood tries to be at around a 7.4. So 10 to the negative 7th power is the hydrogen ion concentration of blood, around that. So if the hydrogen ion concentration if the pH of blood is 6, then that means you have 10 to the negative 6th, or 1 power of 10 more hydrogen ion. You have 10 times the hydrogen ion concentration than you should. if you have a pH of 6 instead of a pH of 7. So in other words, you have too much hydrogen ion if you have a more acidic pH. So one thing the body can do is eliminate hydrogen ions to balance pH. So if I've got too many hydrogen ions, I have an acidic pH, so I can pee out or eliminate or secrete hydrogen ions from the blood. Okay, so anyway, I'm not going to say much else about pH. It usually gets people freaked out when you start talking about base 10 and negative exponents, and so just remember that pH is 7 for now. pH is 7 is neutral. That means 10 to the negative seventh concentration of hydrogen ions. So 0. Then 6 zeros and on a 1, so 7 decimal places, and then anything is with more hydrogen ions is going to be a pH of less than 7, so pH of 6, 5, 4, 3, 2, and 1. And that just means there's more hydrogen, so then we'd have to get rid of it. We pee it out. Okay. We're going to see, though, that's not the primary way. That's one of the ways. The primary means of pH balance, we're going to see next competency 9 with the respiratory system. So anyway, stay tuned for that. So filtration, reabsorption, notice, happens throughout, and then secretion at the end. So that juxtaglomerular apparatus, again, we can see that pardon me, that distal convoluted tubule snug up against the afferent arteriole, and then we can see the efferent arteriole. Notice we've got anything that maybe that's in the blood that's coming into the glomerulus. We can potentially eliminate it right away, because remember that distal convoluted tubule is dumping right into the collecting duct. So if there are things in the blood that need to be eliminated, we can dump them right there. They don't even have to go through the filtration process. Okay, so filtration, as with everything, it comes down to a pressure gradient. So we'll look at pressure gradient. There's the glomerulus is a capillary network. There's a pressure, what we call blood pressure or hydrostatic pressure. They're part and parcel. So hydrostatic pressure and blood pressure are the same thing. But we're going to see that blood being forced into the glomerulus. So that pressure gradient from inside Bowman's capsule and in that capsular space, and where the blood is coming into the glomerulus and basically hitting the wall, the inner wall of itself, and then having that inner wall of the Bowman's capsule connecting or touching. So that blood pressure, and then all these little pores in the wall of the capillaries are going to allow a certain amount of fluid. So hydrostatic pressure is going to force primarily fluid, water from the plasma and a few other things out of the glomerulus or the bloodstream and into either the space or into the glomerulus itself. So anyway, glomerular filtrate, and again 180 liters a day, so almost 50 gallons a day, and we can measure this and call it glomerular filtration rate. So it's determined primarily, so how much fluid per day or per hour rate per some period of time, how much of something per period of time are we able to filter. They call that the GFR, the glomerular filtration rate, and that's relating to the blood pressure, the hydrostatic pressure within the glomerulus, which then is directly related to your blood pressure, to systemic blood pressure. So if you have hypertension and high systemic blood pressure, that's going to increase glomerular hydrostatic pressure. That's going to increase filtration and potentially over time increase the amount of stress that's placed on the capillary or glomerular walls. As the app, so how much? What's GFR? How can GFR be regulated? Well, the body can regulate how much urine or how much plasma we're filtering by altering through vasomotor responses or vasoconstriction, vasodilation. So if we increase the diameter of the afferent arteriole that's going into, so this is what's bringing blood into the glomerulus, if that is large, of course, we're going to have a higher filtration rate potentially, especially if we want to, if we really want it to be high, we're going to combine these two, the highs and the highs. So the large and the small. So the exit arteriole, the efferent arteriole that's leaving the glomerulus and the Bowman's capsule, if that diameter is small, so we've got a large diameter coming in, small diameter leaving, that's going to allow for not only more blood to go into the glomerulus, but less blood to leave. And so it's going to stay there longer. So we can give it a lot. Okay, so just give it more blood by increasing the diameter of the afferent arteriole. And then by decreasing the diameter of the efferent arteriole, we can ensure that it's going to stay there longer. So, so that's what this is trying to show. And then vice versa, if we want to decrease glomerular filtration rate, we don't want as much going into the glomerulus. We just shrink it down, shrink the diameter. Don't give the glomerulus as much blood to filter. Or we can increase the size or the diameter of the efferent arteriole, just open that up so any blood that's in the glomerulus is allowed to leave because there's a much larger diameter tube that exits the glomerulus. So anyway, I think that makes sense. So that RAAS system, renin or renin-angiotensin-aldosterone system, can alter and affect the glomerular filtration rate as well. So, and again, we'll look at that shortly. So the pressure. So we're on the filtration train. Step one of urine formation comes down to basically a very, it looks complicated, but it's a very simple formula. I'm gonna come back to that. It's called effective filtration pressure. So we have a glomerulus and we've got blood pressure or hydrostatic pressure. We would call that glomerular hydrostatic pressure. Oops. That's going to be around 75 millimeters of mercury. So this is basically the blood pressure coming into the glomerulus, exerted by fluid on the capillary walls of the glomerulus. There's something called capsular osmotic pressure. So osmotic pressure has to do with the ability of water to move somewhere to dilute an area. So if an area has a lot has a high amount of solutes, then osmotic pressure is going to be high as water is trying to move to dilute that area. So, so anyway, there are no proteins in this this capsular osmotic space. The fenestras are too small. So hopefully they haven't ruptured or we don't have a breach somewhere. That may have increased or allowed for macromolecules to get into this capsular osmotic space. or capsular space. So anyway, there's no water from this space trying to push in. So we generally see that as zero. So on the one side of the equation, so this is forces that are moving fluid out of the glomerulus. So blood pressure. There's a pressure coming in. So every time the heart pumps, and blood's just rushing, and branching, and then it hits kind of the wall. But this wall has holes in it. That's hydrostatic or blood pressure. So you're going to see that's the main force of moving something out of the bloodstream. Okay. And that's 75 millimeters of mercury pressure going in. So there's a resisting pressure from the Bowman's capsule, call it capsular pressure. So capsular hydrostatic pressure and glomerular osmotic pressure. Okay. So we'll do glomerular osmotic pressure. So pressure generated by the proteins left in the capillaries. So there's still proteins in here. So the osmotic pressure is going to be greater in here as water is trying to leave this Bowman's capsule and enter into and dilute this area. Okay, so basically what we're saying with osmotic pressure is that there's still a lot of stuff, substances, solutes in the blood, and so the water. So there's a higher osmotic pressure because there's more stuff in there for water to want to come in and dilute. Okay, so that's basically what's going on with this glomerular osmotic pressure. That's the pressure coming from the Bowman's capsule and that capsular space trying to push or force its way into the glomerulus to dilute the area. And then we have capsular hydrostatic pressure. Okay, so that's going to be the pressure inside of the Bowman's capsule that's pushing against the wall. So what we end up with is 30 millimeters of mercury of osmotic pressure generated by proteins left in the capillaries that tend to pull water back into the circulatory system. So you see we're pulling water back into the circulatory system, and then hydrostatic pressure just being generated by the fact that there is fluid still contained within this Bowman's capsule. So we can add the forces that move fluid back into the glomerulus on the other side of the equation. So on one side we have the factors pushing things into the tubular system and factors moving things out of the tubular system. As long, and the idea is to get things out of the bloodstream, at least to some degree. So we call this effective filtration pressure. So forces that move things out of the glomerulus tends to be higher than the forces pushing things back in. So we subtract 75 for this particular example. We had 75 trying to push things out of the glomerulus and 50 pushing things back into or against the glomerulus. So we will have movement because there's a 25, we have a positive 25 pressure. Things go from high pressure to lower pressure. So the fact that we're at a higher pressure in here, a plus 25, for instance, is going to enable filtrate to form in this Bowman's capsule. And then we move on into the proximal convoluted tubule. Some of the items that were pushed into, pressured, if you will, into the Bowman's capsule, sodium, glucose, some amino acids, chloride, phosphate, bicarbonate ions, certainly water. So a lot of items that got put into that got filtered out of the blood and into the tubular network or tubular system are going to need to be reabsorbed. Okay, so how do we get sodium reabsorbed? Again, I mentioned it earlier. It's got to be active transport. There's still there's a lot more. There's a higher concentration of sodium in the blood, so we're going to need then in the tubules. So we're putting sodium or reabsorbing sodium from the tubules into the bloodstream. That's going to require active transport mechanisms in the form of a sodium potassium pump, and therefore the presence of glucose to make ATP. So not all of that glucose that made it into this area is going to be used for ATP production. Most of that glucose we need to reabsorb back into the bloodstream. Okay, if we have an excess amount of glucose in the blood, we may not be able to reabsorb all of it, so it's going to escape into the urine. So one of the main testing aspects of a urinalysis is going to be looking at the presence of glucose in the urine. So anyway, so glucose and amino acids are going to be pulled out or pulled out of the tubular system, reabsorbed into the blood via co-transport mechanisms. These co-transport mechanisms are going to be associated typically with sodium. And then chloride generally follows sodium. So phosphate, bicarbonate ions. Remember, bicarbonate ions are for buffering. We'd see these usually as HCO3 when they're their chemical formula with a negative charge. Okay. They are ions, or negative ions, or anions. Chloride's an anion. So these anions are going to passively move into the blood because there is an imbalance of electrical charge. So these guys basically stick with sodium. Wherever sodium's going, these guys are going to go because of sodium's positive charge. And then, of course, water is going to get reabsorbed as well, just by the fact that all of these other substances, all these other solutes are leaving. Remember, water always chases sodium. Water's going to chase all of this stuff out. So, so osmotic pressure increases into the blood. So water's going to follow. Okay, so here's a couple of examples in illustrated form of what's going on here. So a couple of items got filtered out into the tubular system. So we're in the proximal convoluted tubule here. And here's a sodium transporter. And here is a chloride transporter. And here is a pore or a channel, probably what we'd call an aquaporin for water to pass through. And what we're looking at here is this epithelial cells, epithelial border out into the interstitial space and into one of those paratubular capillaries. So what we see is sodium, chloride ions following sodium, and of course water following those two. Now, once we get out of the tubular, once we get out the lumen of the tubule, we get into these epithelial cells. This is where we're going to find the sodium-potassium pumps, okay, as well as chloride transporters or chloride channels. Okay. Aquaporins. So sodium chloride water goes in the interstitial space and then makes it into the bloodstream. Okay. This one's just showing glucose being co-transported. Okay. It gets co-transported out of the lumen and into the epithelial cells of of the PCT. Okay, so there's where the co-transport occurs, and then sodium goes about its same business. The sodium potassium pump, and glucose uh, is going to passively diffuse over into the bloodstream. Okay. We can also do some reabsorption in the loop of Henle, what we call a countercurrent mechanism. So basically, countercurrent just means I've got a tube. It's like your P tube and your plumbing under your sink. Water going out, goes up, and then goes out into the drain line. And we've got a similar countercurrent flow going here. So just means one current goes down, the other current goes up, even though they are connected by this loop. So we see the osmolarity or osmolality of the urine at 300, or of the filtrate. And then all that means is we've got 300 is like isoosmotic. So we're going to get that nice balance of water leaving, urea coming in, water leaving, urea coming in. So we're building and building and building. And notice as we get to a certain level, the filtrate, or the amount, the osmolarity is really high. So what that means is there's a lot of stuff in here. And so the idea is a lot of water is potentially going to be is we're going to end up taking on a bunch of water over here potentially. So it looks like urea has pretty much is done being secreted. Notice urea is out here; it's being secreted. Okay. So we're reabsorbing water. So we're going to continue with moving sodium and chloride ions out of here. Okay, so eventually the osmolarity, or the osmolality of this of the filtrate, or of the tubular fluid, is going to have decreased from 300 to 100. So any fluid that's leaving this loop, that's going now into the distal convoluted tubule, is going to be considered hypoosmotic, which basically just means that there's not a lot of substance in here. There's still some, certainly, but not a lot. So we're not going to get a bunch of water rushing in here to dilute this area. Okay, so it's hypoosmotic. That just means we've pulled a lot of stuff out of here. Notice as we've added all this urea, okay, we've increased osmolality all the way up to 1200. Okay. The urea and water continues to leave as sodium and chloride continue to leave. So that's what it's showing here. And by the time we get over here, so much sodium and chloride has left, and so much water has left, that we've reached a hypoosmotic situation, meaning no more water is going to come in here. I mean, we weren't gaining water anyway. Water was reabsorbing the whole way, because sodium and chloride were reabsorbing, right? So sodium and chloride were reabsorbing this whole way. It's only showing them reabsorbing over here. They're reabsorbing this whole time. They didn't want to clog up the area over here. Okay. Same with urea. Okay. Urea is done. Urea is nitrogenous waste. Okay, so it stops here. Any urea, about hit 50%. So any urea that's left over is going to get secreted from the blood into the distal convoluted tubule. Okay, so again, no more water really is going to be secreted. We're not going to be secreting water into here. That's what that hypoosmotic. If this was hyperosmotic over here, we would continue to get water pulling in here. and secreting from the interstitial space or from the blood. So anyway, the distal convoluted tubules are going to reabsorb that sodium via active transport. Uh, we're going to see reabsorption of water in the collecting duct. Any urea that's in the collecting duct is going to diffuse into that medullary interstitial space. So urea into this area. So we could still have some urea lingering around in that medullary space. The distal tubules and collecting ducts are targeted by ADH, or antidiuretic hormone. That's where we can reabsorb more water if we need to. Okay, so lastly, again, is secretion. So reabsorption, step 2. Step 3, tubular secretion. Again, moving things out of the blood into the fluid. Again, usually it's going to be excess nitrogenous waste that needs to be pulled, ammonium ions, okay? Hydrogen ions, again, to decrease blood pH. We want to increase the amount of hydrogen that we get rid of. I guess decrease the acidity, increase, you know what I mean. We want to get rid of some of our hydrogen ions so we get our pH closer to neutral. Okay, so we can eliminate hydrogen ions. Tubular, this is that aldosterone spot as well. These are where we're going to be targeting hormones that, allow for an increase in potassium secretion and therefore an increase in sodium reabsorption, therefore an increase in water reabsorption. So aldosterone helps to, along with antidiuretic hormone, helps you to retain water, increases your blood volume, and again, makes the body less acidic, the secretion of hydrogen ions. So anyway, that's pretty much it. I just want to, there's that again. And again, it's that ADH that's influencing water reabsorption. ADH, antidiuretic. It reduces water loss. It works with aldosterone to do this. That renin-angiotensin aldosterone system helps angiotensin helps with for vasoconstriction. It increases blood pressure. When we need an increase in blood pressure under stress, aldosterone helps the body retain water when we're under stress because there's more friction. There's more of a need to retain water to hydrate and to help with pH balance. Again, under stress. So anyhow, once all of that kind of settles down, the stressors are over, we can kick in atrial natriuretic hormone. So that's coming from the right atrium. I believe the left atrium too. I'm not exactly sure, but it basically works with, it promotes sodium loss. So once the parasympathetic, the vagus nerve, and the sinoatrial node convert back to normal rhythmicity, again, parasympathetic resting, normal homeostatic rhythms, that will trigger atrial natriuretic hormone to be released, go to the kidneys, tell them we need you to secrete, we need sodium secretion, therefore water will follow. Sodium secretion remember, secretion is from blood into urine. So sodium will be drawn out of the bloodstream into the urine, water follows it. So ANH is a diuretic. Okay, glomerular filtration rate. We've got mechanisms again that I mentioned earlier. We can vasodilate, vasoconstrict, afferent and efferent arterioles and get some sort of action occurring there. Again, that juxtaglomerular apparatus, we can pull things out of that afferent arteriole before they even enter into the glomerulus. Um, yeah, myogenic mechanism, so muscular aspect, achieving rapid, effective regulation of the GFR and afferent muscle contraction and relaxation. So again, going back to um, the efferent vasodilation or vasomotor responses, the glomerular, juxtaglomerular apparatus. So anyway, what's ultimately gonna be in your urine? So now that we've filtered, we've reabsorbed, we've secreted, what's left? What's gonna come out? Well, primarily nitrogen. Well, there's water, of course, but nitrogenous waste, which again comes from protein metabolism, comes in the form of uric acid, urea, ammonia, creatinine. We're going to lose some electrolytes. We are going to lose some sodium, potassium, ammonium, chloride, bicarb, phosphate, sulfate. Those things are going to be present. Certainly toxins are going to be in the urine. Pigments, urochrome is what gives urine its yellow color. Hormones oftentimes are going to be eliminated from the body through the urine. And then some things we don't want in there: blood, glucose, albumin. Those could all be signs of kidney disease. Those fenestras in the glomeruli are ruptured, or anything and everything is entering in. So anyway, I put this in here as a dipstick. We do these in face to face. We can check specific gravity, the pH of the urine, leukocyte activity. That again, there shouldn't be white blood. There shouldn't be any blood in the urine. Okay? If there is, we have, depending on the color, how much. Nitrites, ketones, bilirubin, urobilinogen, proteins, glucose. Again, there will be some glucose. There shouldn't be any of these big proteins. Urobilinogen, there'll probably be a little bit of that. So anyway, this is a 10 strip. I think 2, 4, 6, 8, 10. That's it. Hope you enjoyed another round of advanced A&P videos, and Competency 9 video will be coming out soon. Let's see, PhysioX Activity 6. And then I'd like to also put out the PhysioXs for the urinary system too. So stay tuned and have a great day.